Good morning. We're gonna review what we were doing in chapter 2 today. So on the board we have an implicit differentiation question. The function is being given by equation instead of a formula. So we were supposed to find the derivative of the left side and the right side. So that way we can find the relation that allow us to calculate the derivative. So we provides a formula. When we differentiate both sides of the equation, I think we're okay with differentiating 3x squared using power rule. The power 2 multiplied with 3 and the power 2 minus 1, we will have 6x. That's the derivative of 3x. When you're differentiating 5y squared, you will apply power rule again, so it's going to be 10y. But y is a function, so y behaves like inside function. So when you're differentiating the y term, you have to multiply y prime. That is dy dx, that's derivative of the function. So this is caused by chain rule. So the first one and the third one, we can apply power rule and chain rule. The middle one, because this has x and y, you have to apply product rule. So that for us, we sometimes, if you want to be detailed and step by step, you will indicating your differentiation rules using this kind of notation. So we will say this is negative 2x times y. So you differentiate negative 2x, multiply y, plus keep the negative 2x, differentiate the y. Then it says y, and then the differentiation notation there is just indicating which part is supposed to be differentiated. And this is already done. The first one, the third one is done. So it's a little two. You know, spend a little bit of time. If you're done, you can see the same thing as here. If you're differentiating the negative 2x, it's negative 2. If you're differentiating the y prime, it's just going to be y prime. So y differentiated is y prime, or it is the derivative of y. Right? And then once we get that part, we would try to figure out a way to simplify and then have an actual formula for the y prime. Let's see if you already have your answer. Laura, this is a plus sigma y squared. Plus so that is yeah, don't really just one. This is actually the axis is right. So this is actually 5y minus this. So just down. Thank you. Let me finish the calculation here. So after we finish the calculations, we'll have 6x minus 2xy prime and minus 2xy. Oh, there's no prime over here. We'll differentiate the negative 2x, so we'll have negative 2. So negative 2x has derivative negative 2. And the last term is plus 10y. So that's when we finish the differentiation, and we realize we need to combine the term that has y prime. We're going to leave it at the left, and the one that has no y prime, we're going to move it to the right. So let's see, the one you are keeping it is negative 2xy prime plus 10y prime. And the one moving to the right, the negative 2y, you add a 2y to both sides of the equation to cancel the negative 2y. So you have positive 2y. And the 6x, you have to minus 6x to move it over. So it's going to be minus. That's what I was saying. Whenever we switch sides, they always become opposite side. That is when the combination is through submission or subtraction. If it's being combined into the equation with multiplication or division, then of course you should be dividing or subtract or dividing or multiplying. But in this case, they are either subtraction or addition. So therefore, most of the time, all we are doing is changing the signs from negative to positive or from positive to negative. This is what we have. We'll factor the y prime out, so negative 2x plus 10y, and multiply by y prime. That's the left side, 2y minus 6x on the right side. So now we have a formula. Y prime is equal to 2y minus 6x on the numerator divided by negative 2x plus 10y on the denominator. We realize that there's common factor and that it doesn't look like at any of those choices. We have to factor out common factor between the numerator and denominator in order to determine the final answer. Let's see. Can confirm the solution. It's the signs as we work through the equation. Sometimes it's really easy to make small mistakes. The sign. All right. Let me finish trying to find the numerator and denominator. These are all even coefficients, so that we realize that 2 is a common factor. So we factor out the common factor of 2. For example, if in the numerator, if you get 2 out, you will have y minus 3x. That's the numerator if you divide out the 2. The denominator, if you take out the 2, you will have negative x plus 5y. All right. Of course, this 2 is a common factor, so we cancel the common factor, and that's supposed to be y prime. Y prime. So the y prime is equal to a division between numerator is y minus 3x. The denominator would be negative x plus 5y. If you want to, you can write it as 5y minus x because it's the same way. See? Let me switch back to page 2. Anyone else? You have your Jose? So the final answer is B. Let's see who has Austin. I think the A was you. Austin.
Okay.
Thank you. This is today's attendance. Do you have any homework questions? Yes.
Yeah. Let me just see if I can read real quick. I can use some help on section 2.5, problem 5.
Alright, so let's see, this question is serial application. 2.5, so so number one thing is the division, right? If you are differentiating division, you either use quotient rule, which is taking the whole structure of division. So the number one rule you have to apply is quotient rule. Now, or you can write as 7 times logarithm to the power -1. That way you can apply power rule and chain rule for the solution. So quotient rule or chain rule, depending on how you change the format of the question. So both of them are the same, so you can try both ways. So then, let's say we're using quotient rule. That is we are not simplifying the function. So my quotient rule will have that kind of x equal to, according to quotient rule, we are supposed to square the denominator, which is going to be ln of x squared plus 3. And that is being squared on the outside. That's the denominator. Let me turn this off. We will square the, we'll try to find the derivative of the numerator, but this function, the derivative is a number. A number, if you find the derivative, is 0, right? 0. So 0 times logarithm, which basically is 0. I'll just go ahead and write 0 minus. So in the numerator of the quotient rule, it's supposed to be low d high minus high d low. So when you're trying to use the denominator multiply the derivative of the numerator, it's 0. So 0 minus, so low minus high d low. High d low, high is the numerator, which is the 7 derivative of the denominator. It's a logarithm that we're defining. This is a part of that. Derivative of the denominator is 1 over the entire denominator. I 1 over the logarithms. The logarithm variable multiplied by the derivative of the inside, which is 2x. That is chain rule. So this is what we have. It's applying quotient rule. So we have fraction inside the fraction. Call this a complex fraction. Normally, if you have a complex fraction, you would try to simplify into a proper fraction. Thus, -7 will multiply the 2x. That gives you -14x. That is the numerator. So this is going to equal to, the numerator is -14x. That's 7 times 2x. And then everything else, they're all denominators. So the denominator will be x squared plus 3 is the denominator because you know it's in the denominator and the numerator. And then the ln also is a x squared plus 3. That is also the denominator. Make sure your parentheses is in pairs. Sometimes I do lost track of them. Realize that this is a pair of the parentheses, which is controlling the input of the logarithm. This is a pair of parentheses, which is controlling that this entire thing is supposed to be multiplied by itself, power 2. So make sure you have parentheses that indicating the appropriate calculation. This is the answer if you're applying quotient rule. I did do a little bit faster because usually I'll write down the quotient rule first and then apply it. And this time I didn't write the quotient rule. If you are not familiar with the quotient rule, you should write it on a page of index card as the formula card that you'll be using for Thursday's test. So for test purposes, you can bring a formula card right on the back and forth, but you cannot use all your notes. So formula card is fine, but formula book is not. All right. So we can also another way to solve this is to use power rule plus chain rule. power rule. Well, actually, we also apply chain rule. Portion, the first portion, there's a chain rule application. Derivative logarithm time the derivative inside. That's already a chain rule. So if you're applying power rule, you first have to have power function. This is that we actually have to change the format of the function. The function is f of x, the original function equals 7 times the logarithm ln x squared plus 3. And then the logarithm is in the denominator, so it's just the power of -1. So a division can be written as power -1, and that way you can start using power rule for the derivative. So according to this, according to power rule, time of x would be equal to, we're applying power rule, then you take the power multiplied by the coefficient, that's -7. So we have -7 multiplied by a logarithm of x squared plus 3. And this should raise it to the power of -1 minus 1. Power rule, the power should be -1, it's -2. Okay, so far that finished applying power rule, because on the outside the power is -1, so we move the -1, multiply by 7, and then the -1 minus 1 is -2. That's a whole process of applying power rule. But they have the inside. If you have 7x to the -1, then the answer is -7x to the -2 power. We're done. But then this inside big thing, so the logarithm x squared plus 3 is the inside function. After we're taking care of the power rule, so it's finishing this, so we still have to differentiate the inside. So according to chain rule, you have to differentiate the logarithm. If you differentiate the logarithm, you would have 1 over x squared plus 3. That's the derivative of the logarithm. So that take care of the ln. Don't forget about ln. The logarithm also have the inside function. So outside, middle, and the inside. So now we have to differentiate the inside function, which is 2x. So the process of applying the chain rule 1, 2, twice. So the first time you finish differentiating this, if I try to write it slower, I would say this part is the answer of trying to differentiate. Let's say we're differentiating logarithm x squared plus 3. Right? This is when you would apply the chain rule for the first time, and then we know that if you are differentiating this, you have to differentiate the outside as the logarithm. All right, then we differentiate the inside, which is 2x. So this equal to this. Therefore, the final answer actually is the derivative of the outside function multiplied by the derivative of the inside function. This is the final derivative. And then we realize this also involves division, involves numerator and denominator. -7 times 2x is -14x, and then x squared plus 3 is the denominator, that's the denominator, and then the logarithm has a power -2, therefore it's a square power 2 in the denominator. So this is a different way to write that same function. So applying power rule plus chain rule, you will have the same answer. Any question?
Hang on, let me just.
Let's see how we can enter them onto web work. I think the power rule format actually is easier to input. So you have -7 times parentheses logarithm princess x squared plus 3 princess to the power of -2. Right, that's the power of -2. If you multiply 1 over princess x squared plus 3 princess, and then times 2x. So this is a directly write down what we have here, and you see the web work that can combine and display format. Oh, we're supposed to calculate F1. That's good. So we don't have to worry about inputting the format. The function input the whole thing actually takes more time. Yeah. The question asks for calculating f prime of 1, not f prime of x. So let's enter. So we're gonna enter f 1 for x. So f of f1 1 is equal to -7 times log this is 1. 1 plus 3 is 4, so it's ln4 raised to the power of -2. And this is 1 over 1 plus 3 is 4. 1 over 4. 2 times 1 is 2. So this is 1 over 4 times 2. That's 1/2. Then this is multiplied by 1/2. Alright, that's pretty much what we can enter. Right. So we multiply the 1/2 with -7, so it's -7/2. And then the logarithm part certainly would be to enter. You can also use your calculator and actually find the number. That's the answer. What?
Yeah, bring the negative to the next one.
-2. Yes, thank you. Okay. So I get to write -2 here. Thank you. That's the process. Sorry about my mistakes. Any questions?
Yeah, let me see if I can get that process down.
So you're doing the same question,
Just,
with different number?
yeah.
Right. If you're on your computer or on your device, you can also try your version of it. Or you can print. You can print a paper copy of all your assignment. So for example, 2.5, you go to problem list and then download a PDF. So you can click on my I can print for everyone's. Yours is a lot less. Just click on the Adobe PDF and you can determine 1 column or 2 columns. You can print the entire thing. So let me try this one. So you can have all 10 questions printed on paper so that you can print with you. And then once you finish calculating, then you can go back to the computer and enter. So this way you don't have to spend time copying. You don't have to spend time copy the question count. At least you have a version of the question, and you can calculate and have the calculation on your notes. All right. Here.
All right.
Personally, when I was working on this, I actually handwritten all the questions in my notes, just so they're in the same place. Question. Which one?
Hang on, wait a minute. Got my thing up here.
Any other questions? This is question 8. Is in 2 plus 6? If you remember, 2 plus 6 was implicit differentiation. So we were supposed to find the derivative using implicit differentiation. Let me try to give a few more examples of this. This is something we should. It's called differentiation using implicit differentiation. The function itself already had explicit formula, but then there's a problem that the function has variable in the denominator, in the base, also in the exponent. That made it harder to differentiate. We did talk about the differentiation formula for exponential function. If you have e to the x, then the derivative would just be e to the x itself. Derivative e to the x, e to the x. But if we have a to the x, a being any other number, any number, so the derivative of a to the x, a is a number, a is a number, so the derivative will be a to the x multiplied by, do you remember? Multiply a to x times ln of a, where we were supposed to chain rule. That's the reason for this is you can write a to the x as e to the ln a to the x. So a to the x can be written as e to something. And because the exponential function's derivative has itself, so e to ln of a to the x has itself. So then the derivative of a to the x also has a to the x, but because it's e to the e to the x times ln of x, ln of a, so this becomes the derivative inside function. So the reason that this one has this is because of chain rule. Right? You can also take this as a formula. So now we have a little problem. What if we have x in the denominator and we have x in the numerator? Now we would have a. Well, what's that derivative? And that is something that's a little harder to do than a simple exponential function. These two, the first two, e to the x and a to the a can be 2 to the x, 3 to the x. I'm just writing this as a formula. You can always follow that formula for the differentiation. But if it's x to the x, then it's not the same as these two, but we can use the implicit differentiation to solve it. For example, we would have, let's say, y equal to x to the power of x. So if you define this as a relation, so for example, if x equal to 2, y equal to 2 to the 2. If x equals 3, y equals 3 to the 3. If x equals 4, y equals 4 to the 4. So you can see this will provide a one-to-one correspondence between x and y. So that's what's defined as a function. But any function, we want to be able to find the derivative, therefore determine the slope of the tangent line. So in order to do that, we will try to find the logarithm both sides of the equation, because the difficulty in the differentiation is that x and x is in the base and the exponent. We cannot differentiate both of them simultaneously, so derivative is not 1 to the power 1. As usual, we have to differentiate this and this step by step. It's kind of like a change of the product, but not in the product format. So what we're gonna do, we find the logarithm both sides of the equation. So we have ln of y, ln of the left side, and ln of the right side. All right, what we want to do is break this format of power to the power. If you have variable to the variable power, then the variable base and variable power, that format made it difficult to differentiate, because we have power rule, which the variable is in the base, and then the constant power. So power rule has a constant power. Exponential function has a constant base. So this way you have variable in both. You cannot apply power or you cannot apply exponential function differentiation. That's made it hard. So I'm going to try to separate them. So if you write it in this way, according to the logarithm property, the exponent inside the logarithm can be moved to the front. They're equal. So basically what we have is logarithm y equal to x times logarithm of x. This is a simple multiplication, so it's not exponential anymore. We're able to convert logarithm allows you to convert exponential relation into multiplication relation. Then we find the derivative, because if you have a multiplication, the derivative of a multiplication is a product rule. So we can strictly apply product rule. We can have a any rule is better when there's no rule. And then the problem with this kind of thing is we don't have a rule applied to it. So we can change it the format so that it looks like a multiplication. So now we're gonna differentiate both sides of the equation. So we will find the derivative of the left side. See y equal to this. So your y prime must be the derivative. So we find the derivative of the left side. What's the derivative of the left side? 1 over y and
Times y prime.
times y prime. Yes. So the derivative of the left side is 1 over y times y prime. That's the derivative of the logarithm times and then triangle and logarithm differentiation. This side we apply product rule. So you're going to differentiate the first one. That's 1 times ln of x. So we have ln of x plus this time we're going to keep the x, but differentiate the logarithm. If you differentiate the logarithm, it's 1 over x. So that side you keep the x and then times 1 over x. Okay, so essentially we have 1 over y prime is equal to ln of x plus 1. X times 1 over x equals 1. This is x over x. X times 1, x over x, which equals 1. All right, now we're almost done because our ultimate goal is to find the y prime. So all we have to do is multiply both sides of the equation by y. So we will have y prime is equal to y times ln of x plus 1. The original function is explicitly defined, so your derivative should be explicitly defined, so that y has to be switched to x over x power. So we will have y prime is equal to x to the x power times logarithm of x. So that's the derivative. So it follows similar pattern that exponential function has a derivative that has itself and then multiplied by the derivative of the inside function sort of thing. So this is the method we're using to answer the question. The derivative of this one is equal to x to the power x times ln of x plus 1. I'm just trying to introduce this so that we can work on the number 8. The number 8 is not x to the x. I'm just saying that this kind of approach is commonly called log differentiation. So you first take a logarithm because you want to take you want to take care of that thing that there is a derivative here, there's x here, there's x there. So then a variable to a variable power, a variable term to a variable power. That's what's making it complex, and then by taking logarithm, we are dealing with this kind of situation, right? So this is our example. So applying this kind of idea, we're gonna work on this one. So this one we have y is equal to 5 times. We're gonna repeat the same process. Sine x to the x power. So this is the original function. And we are going to take logarithm of the left side and the right side. The idea is that we hope to find a simple derivative. I realize the 5 is in the way. All right, I'm trying not to take the 5 with us everywhere. When we try to take the left side and the right side, the 5 it's gonna be making things more longer. So if f is defined like this, that f prime of x is equal to 5 times the derivative of sine of x to the power x, this term's derivative. Okay. So as long as we can find the derivative of this, we multiply 5, that will be it. That's why I don't want to carry the 5. So let's try to find the derivative of sine x to the x instead. All right, so we define y equals sine x to the x power. All right, so one thing we got to remember is that the actual derivative, the answer for the y prime, have to multiply by the 5, so that carry the 5. So we start from here, we're going to take logarithm both sides of the equation. So we have natural log of the y, and then natural log of sine x to the power of x. According to the power rule of logarithm, the power would always need to move. This is not differentiation. This is a rule for logarithm property. Whenever you have a power in a logarithm, the power it's okay to move it to the front. We do this because we prefer a multiplication relation rather than the power to a power relation. So let's move this one to the front because it's easier to find the derivative. So then we have ln of y is equal to x multiplied by logarithm of sine x. And then now they are two separate functions. So this function is function x multiplied by logarithm of sine. It's another function, they're multiplied. All right, so far we define the y, we find the logarithm of, and then we revise the logarithm. So far this all unchanged format. And now we're going to actually find the derivative. This is not derivative calculation yet. And starting from here, we're doing implicit differentiation because we're hoping it will provide some information of the y prime. So this step is the key that we are doing implicit differentiation. So we differentiate both sides of the equation above. So we're going to differentiate both sides of the equation. If you find the derivative of ln of y is 1 over y because of logarithm, and then y prime because of the chain, which equal to. All right, now it's time to differentiate this. Normally, I will differentiate the x, but keep the logarithm term. So if you differentiate the x, equal to 1. So that's 1 time the logarithm. And so the first part will be kind of differentiate 1, keep the other one. So we're going to keep the logarithm. I'm differentiating the x time. We're going to keep the x. We're going to differentiate the logarithm. That you're going to have to apply chain rule because there's a sign inside the log. So differentiate the log, you have 1 over the sine. Differentiate the sine, you have a cosine. So always differentiate the outside function first. If you differentiate the outside function, it gives you 1 over sine x. That's when you finish differentiating the ln. Differentiating ln, that gives 1 over sine, and then the inside function is logarithm, and the inside is the sine, the root side is cosine. This is going to multiply cosine of x. All right, and then realize that cosine multiplied 1 is cosine over sine. Cosine over sine is actually cotangent. So now we have 1 over y prime is equal to logarithm ln of sine x plus x by cotangent of x. Right, so that's 1 over y times y prime. If we want to find the y prime, we're going to multiply the denominator to y. So y prime is y times everything on the right side is ln of sine of x plus x times tangent of x. That's the y prime. We cannot enter this. This function is being defined as the x variables. We're going to write that the y equal to x sine x to the x, so y prime equal to sine x to the power of x. That is expanding the y. We can't keep the y notation there. We have to rewrite the y. This is how y is being defined, so that is multiplied by the rest. Okay, so that's our y prime. This is the derivative of this. So you can see as these things are gets more complex to look at. Now the final answer to the question is f prime of 2. But remember, we also have to multiply the 5. So the f prime, remember the 5. So f prime of x is equal to 5 multiplied by all we were getting. So 5 times sine x or of x. This is multiplied by ln of sine x plus x. All right. Any questions so far? It says we want to find f prime of 2. We have to plug in 2. And you can use your calculator, or you can just enter into the whole formula. So the f prime of 2 is equal to 5 times sine 2 raised to the power 2, and then multiplied by a summation ln of sine 2 plus cotangent 2. Right, and 2. All right, let's see how it works. Double check. So it looks like it's okay. It's like negative 4.1771, but enter the calculation is also okay. That way I don't have to worry about rounding. Whenever I use a calculator, I have to kind of guess, should I use 4 decimal or 6 decimal? But if you enter the calculation formula, we don't have to worry about. As long as the formula is right, the answer is right. So I kind of would use this more often. Any questions?
Can
Yes.
you show the word again?
Okay, it was it's an implicit differentiation. I did leave the 5 some if you try the example on YouTube, the implicit differentiation using the logarithm differentiation, sometimes you keep the 5. If you define this as your y, say I define the y equal to sine x with x. If you have 5 here, when you are taking the logarithm, then you have logarithm 5 plus logarithm this. And then when you're differentiating, of course, logarithm 5 is a number, which has a 0. So, and then if this is the y involve the 5, and then when you try to plug in this y, there will be a 5 here. So that also partly affect how you answer the question. Any other questions? Other questions? So you want to know the cotangent value, and we'll do tangent of 2. 1 divided by tangent 2 is cotangent 2. So 1 over tangent 2. Oh, U has 3, right? Okay. Any other questions? Yes. 2.7. Okay. All right. 2.7 work with the inverse functions derivative. And we didn't mention that the derivative, which is the slope of the original function, and the derivative of the inverse, they're reciprocals. So this one thing that's really important is to realize they're reciprocal. So we're going to calculate g prime of db and g prime of b. G is the inverse function of this function, where b equal to 1. All right, b equal to 1. And then g the inverse. For the inverse function, the original function would map the x value to a y value. Now, the inverse function will match the y value to the x value. So this b equal to 1, this 1 is not a x value. It is actually a y value. You're going to try to figure out 1 equal to x plus cosine of x. What kind of x will give you a 1 here? And all right. So we can let me copy this question. Think about the appropriate value for b. Okay. So try to understand it. G is the inverse of f. Now f. So we are trying to. So then G of b. We're going to calculate G of b. So b is the input for G. If you want to calculate G of b, G is the input for G, and G is the inverse. So the input for the inverse is actually the output for the original function. So b is the output, or the y value, the output value for f. And try to logic that this b, which is b equal to 1, the 1 is actually a y value for the f. So basically that what it will remain is 1 equal to x plus cosine of x. Right? So here's the thing, cosine of x will always be less than or equal to 1, right? So if we want the 1 equal to this, then both of them has to be less than 1. If x is less than 1, how can we make this equal to 1? Just think of the number. So one thing we do know is that if x equal to 0, this will be true, right? This cosine of 0 equal to 1. Cosine always start with 1, right? So if x equal to that 0 plus cosine of 0 equals 1. Cosine of 0. I mean, you can use your calculator, make a degree measure, or really measure cosine 0 equal to 1. So 0, this is really 0 plus 1, which is 1. So that is saying that 0 is a solution. Now, this is a function that has the inverse. If a function have an inverse, for each output, there can only be one input. Since 0 is possible for this equation, we don't have any other value for it. So we know for sure that the input is 0, the output is 1. That's okay. So we know this is the answer for the inverse. So this first question, the answer is 0. Well, another way to say this is because b equal to 1, we know that question says b equal to 1. So what we really find out is g of 1 equal to 0. Now we say g of 1 equal to 0 because f of 0 equal to 1. F and G, they're inverse of each other. Input, output. For G, this is output, inputs. You plug in the 1 for the inverse, you always get 0. And that's the meaning of inverse function, right? Inverse function switch input and output. First question, first part. Does that answer the question? Right, so this is the answer to the first one. Then let's try to answer the second one. Now we're trying to find the derivative of this function. Remember, the derivative of this function is inverse of derivative of this function. So all we have to do is find the derivative of this function and flip it. All right, so we're going to try to find the derivative of f. F prime of x is equal to, all you have to do is find the derivative of the original function, which is 1 plus, what's the derivative of cosine?
Negative sign.
Negative sign, so it's 1 minus sine of x. That's the derivative of that is the derivative of the original function of the f function. Now remember, the input is 0, output is 1 for the original one because we switch input and output. In the inverse is 1, 0, for the original is 0, 1. So we're going to plug in 0, the original input, the x value, to make sure we don't plug in the wrong value. If you plug in 1, it will be wrong because switching the input and output. So we're going to plug in 0 here and actually find the derivative. So f prime of 0 is equal to 1 minus sine of 0. Sine 0 is 0, so this is really equal to 1. That's the derivative. So then we're going to try to find the reciprocal. The reciprocal here is going to be 1 over 1. The reciprocal 1 is still 1, right? Are we okay then? So this is 1 over 1, or reciprocal 1. The answer is 1 here. It's the second part. So answer to this question is 0, 1, 1. 0, 1. Now, if you want to have a better understanding of it, you can also graph the function, and then we can see how it relates. Okay, so we have y equals to x plus cosine of x. How it is. And we are trying to find at a point when the b equal to 1 and equal to a y value. So you're going to draw a line at y equal to 1. All right, so y equal to 1. And that's this point. You see the slope is 1. So if you are trying to determine the tangent line, y equal to 1 times x minus 0 plus 1, because the point is 1, 1. That's how it looks like. All right, so that's the tangent line. And then we want to find the inverse function. It's a little hard to find the inverse formula for this. This function is 1-to-1, so it definitely has the inverse. I'm going to write the inverse. So to find a explicit formula for the inverse are going to be hard. But we can find the formula for the. We can find the formula. If you want to find the formula for the derivative, you have to switch the input output and do implicit differentiation. Hope that kind of answered your question. Slope equal to 1, and then the value equal to 0 leads to the x value. The inverse x equal to 1. I can only graph the original function. You cannot graph the derivative. The inverse is not inverse. Any other question? Any other question? We can look through all the rest of the questions on some just to have a better understanding of the derivative inverse. Question 1. All right, question 1 says, for each of the given function, find the derivative of the inverse. So f F inverse, find the derivative of the F inverse at a given point C. First find A equal to F inverse of C. So C is the input for the inverse. C is also input for the derivative of the inverse. So C must be a input to the inverse. Therefore, it's an output for the original. So C is actually a Y value there that we're trying to find out. C is a Y value, A is a X value for the original. All right, first question. This is how the function is being defined. And now one of the things that we have to understand it for sure is what does C exactly equal to? And I know that C is input for the inverse, so it must be the output for the original function. So we're going to have to determine how can you get a negative 15 out of this function. And that's the number one thing we have to identify. That is to identify the A. This is the first question on the 2.7. So we'll try to type it. C is the input inverse. And then A is the output for the F inverse. That's how it's being labeled, input, output. Input and output. So this is input, this is output for the inverse. Therefore, C must be the output. C is the output. That's the meaning of the inverse. Out for F. And A is the input. So to make it clear that we will have F of A equals C, right? So since C is the output, so then now we were supposed to have F of A that's equal to C. For example, for the question part A, we would have F of A that equal to C. C is negative 15, negative 15. Right, that's what it is. So you identify where does it belong? Does it belong in here? Does it belong in there? The negative 15 is the output. So if you want to find the A, you have to look at the definition for F of X. How can we pick the X value, which is the input? X is the input, which is A. How can make that X equal to? So then the F of X will actually equal to negative 15, right? That's how we determine the A. So what should be a possible A here? How do we get from 5 and 10? So then we get negative 15. Right, A has to be 1. But if A equal to 1, 5 times 1 plus 10 times 1, that's positive 15. Negative 1, right? So that's how we determine the first one. If we are clear of how is A X or Y, is C X or Y? C has to be a Y value. X has to be A has to be an X value. That way we can see how we can plug in a number to have the output negative 15. That's how we answer the first question. Then we're gonna try to answer the second question. Second question, we already knew that we're trying to find the derivative value, but it's not the derivative of the original function. It's the derivative of the inverse. In my family, since I don't have a formula for the derivative for the inverse, I try to find the inverse from that. That's really difficult since it's a power 15 polynomial. But we can definitely find the derivative of the original using the power rule, and know that the derivative of the inverse is a reciprocal of the derivative of the original. So if you can find the derivative of this function, do a 1 over that. That is the derivative of the inverse. So all you have to do is to find the derivative function. That is, according to the power rule, it's going to be 5 plus remove the power over 5 plus 150x to the power 15 minus 1 is power 14. So that's the derivative function. I'm going to plug in the input. The input is -1. So I'm going to find f prime of -1. It's 5 plus 150 times -1 to the power of 14. And -1 to an even power is 1. So it's 5 plus 150. 5. That is the slope of the original function. So the derivative slope of the inverse will be reciprocal. So answer to this question will be 1 over 150. Okay, one has a super large slope. So the inverse must have a really small slope. This is the answer. Question. Many of these questions, it's really difficult to find the inverse function, but we're actually able to find the slope of the inverse because we have that. We gotta be reciprocal. Part A. Any question? Right, try on your version of it, the 1, 2, 3, 4, and then you have. Okay, so similar logic for this one. We have the output is 8. So in this calculation, we're gonna make this y value equal 8. Remember, 8 is a y value. So so we're gonna have to find how can we make this equal to 8. Remember the C, the 8 is actually a output. It is input for the inverse, therefore it's the output for the original. We're gonna make it therefore function's y value equal 8. It's not as easy as this one. We did figure out the -1 through observing 5, 10, 15, then we see that a relation there can be directly related. The 5 plus 10 is 15. So you realize if x equal to -1, we will answer the question. And this one is not so simple. We don't know how to make it equal to 8. We kind of have to solve it. If it's not immediately derived or devised, we can't determine the x value by looking at it, then we have to solve it. So we subtract 8 from both sides of the equation. We'll have x to the power 2 minus 17x plus 74 minus 8 is 66. Okay, so can we factor 66 to get 17? 6 and 11, right? 6 times 11. 6 times 11 is 66, right? 6 times 11 is 66, but 6 plus 11 is 17. So you can factor, to find x minus 6 and x minus 11. So there are two numbers we find x equal to 6 or x equal to 11. But here it says this is the interval. Since we're only looking at the interval 8.5 to infinity. The reason that we have to determine the interval because the function here is going decreasing and increasing. So the function itself is not one-to-one. So we kind of have to take only part of the function. Because if you take the entire function, it doesn't have the inverse. If you only take part of it, maybe it will be one-to-one. Only one-to-one. So that's necessary. And because that is that requirement that x value will be higher than 8.5, we can only take the 11 because if it's 8, if it's 6, 6 is not in the interval. So that is how we know we are going to use 11 as a input for the fx. Therefore, it is a output for the inverse. So the inverse function, you plug in 8, the output will be 11. But for the f, the input is 11 and output is 8. Input out, we switch them. So the answer 11 for part 1. Second part is calculation of the derivative. We're trying to find the derivative. We would find the derivative of the original. X is equal to 2x minus 17. All right, and then let's calculate value at 8, at 11 at times 11. 11 is the input, 8 is the output. 2 times 11 minus 17 should give you 0.5. So the slope for the original function is 5. So the slope of the inverse function is 1/5. The answer for part B. And I finished also part of question 1. So again, this is an example that illustrates the relation between the slope of the original and the slope of the original function and slope of the inverse function. When we try to differentiate the inverse function, this relation always provides some insight on what can they be. Instead of trying to find the inverse function itself, we just find the derivative of the inverse. Kind of like a technique, it made many things that impossible possible now. All right, I hope that start you with the 2.7 assignment. And remember, we're getting ready. We're trying to wrap up chapter 2. If you have any leftover assignment, try to finish them. That should be it for today. Make sure you write down all your homework on paper. Remember, I'm giving extra credit on the test day if you bring your work. I'll see you tomorrow. Thank you.
That one was.
I can email you on me. And if Lauren, I'll email you the
Right, everything. And I can also work on it.
Right. That way you can finish it when you have like that. All you have to just answer the answer. If they're wrong, you mark it out and then start looking at it again. That is more flexible than being glued to the. Yeah. This is the implicit differentiation question that we did. The answer should be how they record it, so if you wonder how it worked out, you can look at the recording.
Are you supposed to like try it? Are you supposed to? Real quick.
Oh, yeah, right after this class. No, yeah.